On the volume.
Yep, you're live now.
Hello, welcome to our most recent machine learning workshop. This is our 5th workshop. At first, we were discussing doing something a little more advanced, but I thought I'd take a step back and just start with a tinkerer's beginning of neural networks. So that's what this workshop's going to focus on. So for a quick overview, I'm just going to give a little bit of a background, and then we'll have examples, and I'll be jumping back and forth between the slides and our examples. And I'll talk about how to connect to the notebook in just a minute. But first, neural networks are based on some ideas that people took away from how biological neurons work. The way biological neurons work is there's a neuron cell with all these dendria coming off of it, and those dendria connect to each other, and all the cells will have large sets of connections to many other cells. And the way that that ends up firing neurons is those connections each can send signals to the cell, and at the cell the signals will combine, and once a certain threshold's reached, the synapses of that cell will fire, causing a cascade event that will go through numerous sections of cells. And people looked at that and thought that that was a good analogy for how to do some more complex mathematical fitting of data and models. And that's where the beginning of all this comes from. So we're going to start with essentially just what's called a perceptron. So before we go into the notebook, perceptron's really basic. As you can see on the right, takes an array of inputs. Each one's called a feature. It multiplies those features by a weight, just a scaling factor, and then it sums them all up, and it passes that into what's called an activation function. Early on, that was just a step function where once the sum of the weighted inputs reached a certain threshold, then it would switch from a 0 to a 1 or vice versa. But there's many other ways that that can be done, including a sigmoid function. So we're just going to play with that first. So to open the notebook, you can go to our GitHub page. It's github.com/SMNIEEE/ML_workshop. Then you can click on the folder that says Session 5. And in there is our notebook. You can click on that. And then when it opens on this page in GitHub, there's a little link that says Open in Colab. So you'll want to click that. And that'll open the notebook in Google Colab for you. But what you want to do is so that you can edit it, save your own copy. You go File, Save a Copy. And now you have your own copy to play with. Part of the point of this workshop is to kind of play around with this stuff. And as you get a little more comfortable with what you're doing, down the road you'll get a little more knowledge as to why certain things are done the way they are. So first thing you want to run is this top cell under the title. That's some basic imports we need to run. Then under the section that says Simple Perceptron, this is where we're going to start. The goal of this here is to bring in a basic data set to create a perceptron model where the features are brought in, a weight is applied, and then a prediction is made on what species out of the 3 species in the data set the data belongs to. So we're going to run through that first cell. That's going to import our perceptron model. Then we're going to load our data in the cell that says iris equals load iris. That's going to be our data set. And you can see the data there. It's quite long. There's some other data behind it, including down at the bottom it says feature names, so you can see what each column is. And it has a target array that tells you what each entry in the array, what the label or category of the flower is. And it can be, according to the target names, Setosa, Versicolor, or Virginica. So that's just some metadata on the data set. So now what we want to do is to assign our data into an input array. So we're going to take just the second and third column, and that's the petal length and petal width. We're going to use that information to try to predict the species of the data. So by running this next cell, you'll create your X data, your input data, and you'll plot it so that you can get an idea of how the X and Y, or how the input features align with the scatter, or the categories of the species. So you run that cell, you'll see a nice little plot here. It's got 3 colors, 1 for each species, and you can see how the petal width and petal length from this data set are associating with the specific species. But now we need to create our outputs. So for building a neural network, just like some of our previous work, you have to have data to train on. So we have some inputs, the X array, and now we need our outputs that we're going to train our model against. So this next cell, what it's telling us is that our outputs are going to be a binary situation. Either it's going to be a Setosa or it's not. So it's either going to be from the blue clump or from the clump that isn't blue. So either green or orange. And it's just going to be a binary yes or no, is it a Setosa? So you run that cell to create your labels for training. Now, the next one, we're going to create an instance of our Perceptron model. We're going to call it is Setosa, since the output of it's going to tell us whether or not a width and length would categorize as a Setosa or not. And then you run the fit function with your input data to train your model. And then we're going to make a prediction. Down in the prediction, we have is Setosa.predict. And I just put in 3 by 1, and you can see 3 on the X and 1 on the Y would be close to a versicolor, so it should say a false for the prediction for is it Setosa. So let's try that. And if you run that, it runs very quickly and you get a false answer. So now you can take some time and play around with different values for your prediction. For example, if you want to try 2, and a 0.5, and rerun your prediction, so I must be entering that one wrong. Oops.
I also got a false for 2 and 0.5.
Yeah, not sure what I'm doing wrong with that. Maybe because probably because I reran the fit function. It's probably,
if you go down to 2 and 0.4, then we can see true.
Then it works?
Yeah.
Oh. So it worked with 2 and 0.5 earlier, so I don't know. I wonder if it's because it's rerunning the fit. Oh, yep. Okay, so that's the basic operation of Perceptron. In this case, we're just delineating between 2 categories. is a setosa or not. It's a pretty simple setup. This is all using the Scikit-Learn toolkit in Python, so it's not even a complicated model. You can build it pretty quickly for any data set. And it's really the most basic neuron to start with, the most basic artificial neural network to start with. So for the second example, we're going to use the same data set, and we're going to do a linear regression with a linear model, just to look at what the weights would come out to be, so you can kind of get an idea of how the weights that are calculated are fitted and match the data. So if you start with this, you'll see that when you look at your model, if you look at the data, you can see it looks somewhat linear. So we're going to play with that and just see what the weights come out to be. So in this cell, we're just going to run it to get a linear regression model and plot it just to see how the petal width and length line up. And you see that there's a pretty good correlation between width and length. So then you could take values from that prediction and then feed it back into your Perceptron and see if those values would work. So for example, we could take new y 5. Let's try this. New x 5, new y 5. So 1.6 and 0.3. We'll plug that back in up in our Perceptron, and that should work. Yep. So now we'll come down here, we'll pick a number we know definitely doesn't line up with the setosa. So we'll get a 4 roughly, which is about halfway through our data set. So we'll say 35. We get about 5.3 and 1.8. We'll plug that back into our Perceptron. And so that one did give us the false that we needed. So using an approach like this, then we can try to predict. We can start with just a petal length and try to make predictions on whether or not something is a setosa simply by generating the petal width based on its length using our linear regression, and then feed that back into our Perceptron, try to make more predictions. Okay, so that's the basis. That's the artificial neural network that everything is built on. It's basically a single neuron that's taking your feature inputs, fitting the weight values so that the outputs align with your training data, and then you can feed it new information into the features and try to predict new outputs. Then we took the regression and we showed that we can fit a line to our data and use that to generate or if we only had one of the two features, we could then make a guess at the other feature and then feed that in and get an idea of a species as well. So now to talk about a full neural network. This is where things are going to be deep if we went into all the details, but I thought it'd be more interesting to just take a stab at going through some basics and then playing with the network to just get an idea of how it works. And then later on, in a later presentation, we can go more into a deep dive of the mathematics and how everything's really working, if that makes more sense. Essentially, we start with arrays of data. Often you'll see the graph like the one on the right, but each little circle there, each node, is really just some input data, an array or a single value. And those numbers, those features, are then connected to a whole bunch of other perceptrons or other types of neurons that are aligned in a layer. In each cell, we'll take in all, or sometimes just a certain number of inputs from the input layer and generate weights and biases, and then apply its activation function to it, and then pass that value onto an output, which will do the same thing again, where it applies weights and biases and an activation function, and then it gives you your output. So you really can think of each one of those cells as kind of like a perceptron of its own, and you're going to start putting them together in a very large acyclic graph like this to generate networks that can make all sorts of predictions. Now, picking the number of layers and the size of layers, the input size is fixed by your data, and the output size is fixed by your data largely. But what you put in between is all customizable, and how you pick that is part of what we call the hyperparameters of the network, where you may want to try different numbers of layers or different sizes of layers, be it, in this case, they're showing 4, but maybe you want 5 or 6. So in this example, we're going to use tools called Keras and Tensorflow. TensorFlow is a framework that is supported by Google. It started quite a while ago, and Keras was a separate API and framework, but as of TensorFlow 2.0, Keras is now integrated into TensorFlow. The point of Keras early on was to make building these models and running them easier, but both frameworks are targeting the same goal, so that's why they've decided to combine. So when you're building a neural network with these tools, some information we're just going to go over, but then we're going to talk about it as we go through the example. Your inputs can be multi-dimensional, so rather than just a single value or an array of values, you could have multi-dimensional arrays of values, like an n by n array that is an image. And the values can be integers, they can be real numbers, but you typically have to process your inputs in some different ways to help the model perform. Typically, you want all of your features to have roughly the same size, minimum to maximum range. If some are on a range from 0 to 255 and others are real numbers from a range of 0 to 1, then that can be a place where the model can have issues. And so to avoid that, we'll try to typically scale everything to be roughly the same range of inputs. The outputs can be a classification example, like the flowers data set that we worked through. It can be represented in multiple ways. There's categorical, where you have, say, 5 outputs, and each one is represents one category that the label could be. Or you could have what's called one-hot coding, which is a little more involved for understanding, but it is also pretty useful. Or you can have regression, like we did with the linear regression. You can build neural networks that fit an arbitrarily shaped line to your data, or some other shape. Maybe it's not even a line. So The outputs can be whatever matches your data set. As I mentioned, there's activation functions in each of the cells. Two of the most common ones are called the sigmoid. We talked about that when we did our workshop on logistic regression. And the other one's called the ReLU, the rectified linear unit, where if the input is below 0, then the output is 0. And if the input is any integer greater than 0, then the output equals the input. So what this would mean is if you passed in the sum of 3 values and the sum was greater than 0, you'd get the sum out, but if it's less than 0, you get 0. Both these activation functions are useful in certain applications. And picking your activation function is also part of the design of the network that matters as you get more involved into these. Once you've kind of thought about how you want to build your network, you have to decide how you want to calculate your loss. Loss is just your error calculation. It's your error term. There's a numerous set of loss calculations that can be done. Typically, for linear regression, you would use something like a mean squared error or some other numerical error calculation. For categorical stuff, it's common to use cross entropy calculation. I put the equation there, but the sense of it is that you multiply your expected value by the log of your predicted value, and you sum that up, and that's a loss calculation. And you want to minimize your loss. These loss functions are designed so that you want to minimize them as you optimize your network, and that will provide you with the shortest path to getting the right coefficients for your weight matrices and biases. Then you have to pick an optimizer. Most people are pretty familiar with a gradient descent algorithm for any sort of optimization, and that works here too. The way that works is it takes the derivatives of each layer and it uses the chain rule to calculate how much each layer changes relative to its inputs. And then it takes the loss calculation you get and it works backwards to adjust the weights to try to minimize that loss. And how much it adjusts it is dependent on how large the loss is and typically a learning rate, another hyperparameter you have to select that decides how fast you want it to try to converge to its final values. But you can run into issues with what's called vanishing gradients when you do this. So it's important that you take into account your overall network and your activation functions and all of these other parameters that you're using as you're building more complex networks, that you don't run into some of these more advanced problems. So with that, let's go back into the workbook and we'll start with this full network characterization. So I did it this way because at least I like to learn by just playing with things, and even if it's on a rough high-level scale to start with, I can learn the details later. If I understand what I'm doing, at least I can play with it more. So in this, I'll kind of walk through the lines as we go through these cells. The first couple lines of this cell, this first cell in this section, is importing Scikit-Learn, and it's grabbing a data set called MNIST, and it's a bunch of images of handwritten digits, and we're going to try to predict the digit based on the image. And so this is just pre-generated data that's available in Keras, and it just makes it easier to work with than trying to download a separate data set. Then we're going to rescale these images. Why are we rescaling them? Because the inputs to the model want the value to be between 0 and 1. But these values, because they're black and white, well, grayscale images, their values are between 0 and 255. So we're going to divide by 255 so the max value is 1. So the next two lines are just printing out the shape, and then we're going to generate just some samples of our data set and plot them to look at. So we'll run this cell, and you'll see this random selection of integers and handwritten digits. Now you can take these print statements and you can go and check the test set as well and look at some of those. And look at the shape, play around with this cell, play around with the data, and get a sense for what it looks like. Each one of these images is plotted in color, but it's really just a 0 to 255. Each pixel is a 0 to 255 value originally, and then scaled down to 0 to 1. And it's a 28 by 28 array. So they're not very big. You can go and look at all 60,000 if you want. I find it handier to do something like this. Randomly grab them, and if you just keep running it, you should get different digits each time. Once you moved on from that, this next cell, we're going to take our training data that we imported above, and we're going to split it into some training data and some validation data. In our last workshop, we talked about the importance of training, validating, and testing your data. So this will split it up, and you can play with that train split. It just tells the function how much of the data that you give it to put into the training outputs and how much to put into the validation outputs. So if you run that, you'll get your data, and you can check the sizes of it. So let's look at the size. So the training data is about 40,000 of the 28 by 28 arrays. If you change this value, you can go, 50, get half the. Yeah.
Yeah, can you make sure you're still set to project or to duplicate?
Sure. It says duplicate.
Linked was just gone. Yeah, cut out for a second. Then it was passing it through. Try. Well, it's got to be giving. If you can get HDMI to the projector, then you're outputting HDMI. I don't know why we lost it here.
I mean, I'm not low on battery.
Back.
Oh, it's back?
Yeah, it's back. It's just this thing being weird.
Oh, okay. Sorry about that, guys. All right, so I'm going to change this back and go back to about 2/3 of the data training and 1/3 for validation. Okay, so we have our data set up. We have our input arrays. We have our output labels. We have a test set that we've reserved for later. So now we got to start building our model. So the first thing we want to do is build a basic model. Now, in the back on these slides, when we looked at it, you see the layers going from left to right, input, then a hidden layer, then an output. That's a sequential model because you have one layer that feeds the next layer, that feeds the next layer, and it goes right in order like a pipeline. So we're just going to stick with that basic structure, which is in Keras is called the sequential model. We're going to instantiate that. Now in here I've put the input layer, which just takes the 28 by 28 array and flattens it out to a 1 by 728 one-dimensional array as the input. And then it passes it to a hidden layer of 100 cells, 100 neurons, using the ReLU activation function. And right now it just passes that to the output layer. Now these are handwritten digits, so there's 10 of them, 0 to 9. And that then has 10 outputs. Now the activation function there is called softmax. And without getting into details, what that does is it scales each output so that each output represents a probability of that particular category being the digit that you're looking at. So, if you have a 5 and it's the number 5 output would be, some probability of it being a 5, say 80%. And that's what the softmax function does for you on a categorical model. So you can run this. And we have a basic model set up. We're going to come back to that. But what you want to do after you've created your models, you want to just look at it, investigate a little bit, make sure it looks right. So you see here our flattening layer converts that 28 by 28 to a 784 one-dimensional array. And then it passes that to the hidden layer of 100 neurons. And then it passes that to the output layer of 10 neurons. And you can see on the right column there the number of parameters that need to be optimized for each one of those layers. And down at the bottom, you see all the training parameters that need to be fitted using our training data. So that's, you wouldn't be able to train something like this by hand, doing hand calculations, because it's just unwieldy. And that's where the strength of this machine learning comes in, is handling these problems that are beyond hand calculation. So if you print the layers, you can now look through them and you can see what the randomly selected weights and biases are for each of the inputs. Now you're probably asking, why are the weights and biases randomly assigned when the model starts and not just all zeros? Well, if they all started at the same value, then they would all optimize to the same value, and you basically have just one neuron multiple times rather than multiple neurons. So when it's generated, the weights are assigned random values as are, and you can select in this model whether or not to assign the biases random values. So you can look through those. You'll see at the very bottom your output array of all zeros. Okay, so the way Keras and TensorFlow work is after you instantiate your model, you have to compile it. What we're doing here is we're telling it to use the sparse categorical cross-entropy loss. And that's the categorical loss mechanism where we try to calculate the predicted output and the actual output in a information entropy sense to get a score for optimizing against. Where you use an optimizer called stochastic gradient descent. Now, the way that's different from a gradient descent is that rather than making iterative changes on each data entry that you pass it, it looks at groups of entries and sums up the errors. So it doesn't try to fit each specific data point, but it tries to fit to large groups of data points. And then the metrics just tell you what you want to look at on the output. So running this cell will create the models, build the model so that you're ready to start passing it data. Down here in training is the model.fit command. This is just like we did with the Perceptron. We're going to fit the data and let the model train so that the weights and biases are as best fit to the data we give it. So you want to run this. I have it in there for 10 epochs, but you could run it for longer. And it'll probably take just a couple minutes to run. Take maybe 10 seconds for each epoch. So you can watch the accuracy and the loss values change here. You can see that the loss is getting lower with each epoch, and the accuracy is going up. All right. So our data is, or our epochs are done. Now we're going to plot the accuracy and loss just to look at how they changed over the epochs. So this next cell is just a way to plot your accuracy and your loss. And you can see that the accuracy for both the training and validation sets starts pretty high, but goes up into the 90% plus range and then flattens out. And the losses start up higher and then quickly come down and start to flatten out. Now you can go back, and I recommend you go back and try playing with different numbers of epochs. That can maybe there's something to be seen further out in time. Also, you can go in and specify what's called a batch size. So rather than it trying to run one sample at a time, it'll run, 10 samples and then do an update. Once you have your model fitted like this, this is where you can now try it on your test set and see how close you can get to your data on your test set. So on our test set, our loss is 0.2067, which is a relative measure, but our accuracy is 94%. That's pretty good. So now what we want to do is go back and start playing with our model. Let's try 300. And see if that does any better. Make sure that took, yep, 300. We'll recompile it, refit it.
Does the free tier of Google Colab still offer GPU resources?
Yep. In fact, I was going to show that here at the end.
Beat you to it.
Yeah. And TPU. You can try out their TPU as well, which is interesting. So with 300, now when we check our test set, our accuracy went up a little bit. So that's just one parameter you can play with. You can also go back and try adding another layer. So let's try that. Let's go back. We'll add a second layer of, say, 100 neurons. Make sure that that worked. Yep. Compile it. Let's run it now. See what happens. What's that?
The model that changed this.
I added another layer.
I walked up to see if I could see it, and it's clearly a bigger model.
Yeah. And this is a pretty basic model to try, but you can play with the different layers and the different sizes of the layers. See how each of it affects your performance. Okay, so now when we check our accuracy, yeah, got another little bit gain, but not nearly as much as we did going to 300 for our first layer's input size, or our first layer size. So now, if you want to have even more fun on this notebook, what you do is you change your runtime type and you change your hardware accelerator to GPU. Because then you can find out if it actually runs any faster. Typically, GPUs are really good accelerators for machine learning because it's all matrix multiplication. And guess what GPUs are good at? Matrix multiplication. So let's try that. Let's see. Run the imports. We don't need to do that portion or that portion again. We'll import our data again. Split it up. We'll build our model, or create our model. Check it. Yep. If you want to look at the weights again, you can. Compile it. And you can see here that the last time we ran it took about 6 or 7 seconds for each epoch. So let's see what it does with a GPU. Not necessarily, because with small models, there's a penalty for loading the data into the GPU and getting it out.
I already tested your model.
Oh, did you?
I cheated my way to that answer. So I think I had a higher tier GPU because I paid for Colab Plus.
Oh, yeah.
So I got a P100, and the difference there in VRAM speed was pretty dramatic because these took like less than a second on each.
Wow. Yeah. This one you're not really getting much of a bang for your buck on the GPU. But this model is pretty small, so you're probably paying the bigger penalty to load your data onto the GPU and execute it.
And I think if they're doing K-series Teslas on the free CPU, the VRAM of those is pretty outdated.
Okay.
Yeah, I don't know what they do for GPUs.
Yeah. Well, let's go try it. Let's see what happens. Change our runtime again. Then we can try Google's own tensor processor. See if that makes a big difference or not.
Just do F5 to run the whole thing.
What?
Hit the F5 to run the whole thing.
Yeah. Yeah, it's not appreciably faster either, so it must be paying too much of a penalty just to use, or not getting enough gain in processing performance relative to the size of the model to make it worth it. Yep, so you get about the same results, but you don't get much of a speed up with the TPU because the model's too small to really benefit from it. But that's essentially how you get started with neural networks. The key now is to play with it more and then start learning more in depth online, or possibly in the future we can put together another workshop where we go over it. So thanks for attending.